All right, so here we have, let us start off with the first question, which is an easy one. So I'll probably skip this one. That reads, what is the difference between speed and velocity? So speed is distance over time and velocity is displacement over time. What is the difference? How is one quantity different from the other? Speed has magnitude only, but velocity has both magnitude and direction. So I'll just skip this one. Okay, then the second question is related to the graphs that we have studied so far. The object starts from certain initial position. Whatever the initial position is, we got to call it the reference point. This is the reference position. This is the line of the reference. So if the object is on one side of this reference point or reference line, displacement would be positive. If it's on the other side, displacement would be negative. Likewise, if the direction of motion is on one side, the velocity would be positive. If the direction of motion is reversed, the velocity would be negative. So here we have two directions. Initially, the ball moves downward, it then rebounds and then goes upward. So initially, the ball goes downward. So let's see what the graph says. When the ball was going downward, this is what happens initially, that the ball goes downward. So this stage represents that part of the journey when the ball goes downward. And all the velocities that they have taken are positive. So according to their convention, downward velocity is positive. Like I told you, in most of the questions, like 9 out of 10 questions, whatever the initial direction of motion is, that is taken positive in the graphs. However, when you're using the convention for the four equations of motion, I said take downward velocity negative, upward velocity positive, and take the value of g negative always, minus 9.81. That was the convention for free fall. Equations for free fall. Free fall equations. Or uh, the equations of motion, which can be used for free fall also. We have four equations. But when you use it for the free fall, when the ball is moving vertically, the convention was velocity downward negative, velocity upward positive, acceleration always negative, minus 9.81 meter per second square. Likewise, displacement above the reference point positive, and displacement below the reference point negative. But the convention for the graphs is, this is what the examiner does most of the times, 9 out of 10 times. Whatever the initial direction is, that is taken positive. Initial direction of velocity is taken positive. Because in this scenario, initially the ball was moving downward. So the direction of the velocity, downward velocity would be positive, and the upward velocity would be negative. So I'll mark the stages, and then you have this instant where the ball hits the ground. Then you have this instant where the ball bounces off the ground. Then you have this instance when the ball reaches maximum height. Then you have this instance when the ball hits the ground once again after the first rebound. So these are the key points. Initially, you can also say this is a point when the ball was held at the height initially, at the maximum height, but it was held there before the motion started. This point is not included in the graph. From here all the way down here, this thing is not part of the graph. This thing is not part of the graph. This vertical line is not part of the graph. So matter of fact, they should draw it as a dotted line. So I'll make it a dotted line, at least for first few examples. So you would know that this vertical line, not exactly vertical, but this line is not part of the graph. And the line is slightly tilted because there is collision time also. The time at which the ball hits the ground was, if I could read from the axis, the time at which the ball hits the ground, this one is 1.1 second. This time is 1.1 second. And the time at which the ball bounces off the ground is 1.2 second. You can read it from the graph straight away. Then what is the collision time? How long does it take for the ball to change its shape, to compress and then expand again before it takes off from the ground? The answer is the difference of these two times. So the ball would take 0.1 second for all of that, which is known as the collision time. And there is energy loss as well, because the peak of the graph keeps decreasing. So we can say there is energy loss also. If the energy is decreasing, kinetic energy is decreasing, then the velocity of the ball would also decrease, which you can see from here. What are these exact values? We can figure out afterwards if we have to, but let's move on to the first part. Air resistance is negligible, which in most of the questions of kinematics, they say this one, air resistance is negligible, which means acceleration would be uniform. And that acceleration would be 9.81 meter per second square. It would be uniform. Without calculation, use figure 2.2 to describe the variation with time of the velocity of the ball from 0 to 2.1 second. We have to comment on the velocity, and luckily we have the velocity time graph. So we can comment directly. The tricky part is when the graph is displacement time and they ask you to comment on velocity. Then you have to comment by finding the gradient. But this one is easy. Let's see what happens to the velocity initially. If I could take a look at this part, the initial stage from 0 to 1.1 second, my velocity is increasing with uniform acceleration. So we write it over here from t equals to 0 to t equals to 1.1 second. Velocity increases with uniform acceleration. What happens after that? After 1.1 second, we ignore the vertical line in the middle because this is not part of the graph. The second stage starts from here, from 1.2 second till 2.1 second. We're referring to this part. From 1.2 second till 2.1 second, the velocity is now decreasing in the opposite direction. Velocity decreases in the opposite direction. And once again, the velocity decreases, but does that decrease with uniform deceleration or non-uniform deceleration? For that one, we can simply see that we have a straight line. So it decreases with uniform deceleration. And you see, the magnitude of deceleration and of the acceleration is same. Both are constant, first of all. So if the acceleration was 10 meter per second square, the deceleration would also be 10 meter per second square. How do we know? Because the gradient of these two lines would be same. Then why do we call this acceleration and the other one deceleration? The upper one is acceleration because velocity starts from 0 all the way to 10 point something. It increases. Why do we call the lower one deceleration? Because the velocity starts from minus 8 point something and it ends at 0. It starts from minus 8 point something, keeps decreasing, keeps decreasing all the way to 0. That's why we call it deceleration. So these two are parallel lines, so the magnitude of acceleration and deceleration is same because their gradients are same. Let's move on to the next part. Calculate the acceleration of the ball after it rebounds from the ground. Show your working. Calculate the acceleration of the ball after it rebounds from the ground and show your working. Now let me find the point After which the ball rebounds from the ground. It is this point, the point where the ball bounces off the ground. So I need to find acceleration after this. So for this one, this is the initial point which you can take, and you can take this the last point, and you can find the acceleration in at this stage. Or you can take any of those 2 points. You can take these 2 points, because whenever you have a straight line, any 2 points that you take, it would be same, the answer would be same. Let me write the formula of acceleration first. And let me take this one as the initial velocity and the velocity here as the final velocity, and I can take the value of t from 1.2 all the way to 3 seconds. But what is the initial velocity? If I could read through the graph, it would be minus 8.0, then 8 minus 8.4, then minus 8.8, then minus 8 point, sorry, minus 9.2, then minus 9.6, then minus 10. So we are at the second block away from minus 8. So the initial velocity is minus 8.8. And the final velocity at the top is plus 8.8. And how long does it take from this point to that point? It takes from 1.2 seconds till 3 seconds. We can subtract those two. So final velocity was 8.8 minus the initial velocity was minus 8.8 divided by time. So the time is from 1.2 seconds till 3 seconds. So what is the difference? Okay, let's move on to the next part. Calculate for the ball from t equals to 0 to 2.1 second the distance moved. So how do we find the distance? Well, we need to find the distance from 0 till 2.1, but in the middle we have two shapes. This is the first shape, which is a triangle from 0 to 1.1. The triangle ends at 1.1. Although you could see in the middle that the dotted line ends at 1.15. But like I told you, the dotted line is not part of the graph. So ignore that one. The triangle ends at 1.1. I'll find the area of that triangle. And the lower triangle starts from 1.2. The triangle at the bottom, it starts from 1.2. The lower triangle starts from 1.2. So you need to find the area of this triangle and the area of this triangle. How do we find the area of the upper one? The area of that triangle would be 1 over 2 into base into height. So let me write down the formula. 1 over 2 into base. What is the base from 0 to 1.1? Base is 1.1. What is the height? 10.8. You get one answer from here, which would be, I think, 5.94. meters. Then you find the area of the lower triangle. 1 over 2. What is the base of that from 1.2 till 2.1, which is 0.9? What is the height of this triangle? 8.8. We don't use the negative sign here because we have to find distance. Distance cannot be negative. So for the second area, we get the answer 3.96 meters. What is the total area? Sorry, what is the total distance? 5.94 plus 3.96. Total distance would be 5.94, which was the distance as the ball goes downward. It covers the distance of 5.94 meters, and after the rebound the ball goes up and covers the distance of 3.96. But we need to find the total distance. We simply add them. Distance, the values of distances, those are always added, they are never subtracted. So the total distance in 2SF can be 9.9 meters. However, if the question were to find the displacement from the initial position, so the displacement would be, if this one was your reference, then the displacement would be only this much, the shortest distance from the start point to the end point. So this x would be your displacement. Or in simple words, if you need to find the displacement, the distance that you get above the graph and the one that is below the graph, these two would be subtracted. So 5.94 meters minus 3.96 meters. And what do we get here? Get 1.98 meters. Or in 2SF you can write it as 2.0 meters. So in order to find the displacement, the area that you get, the distance that you get from above the axis and the one that you get below the axis should be subtracted. And likewise, they asked you to find the displacement till 2.1 second. If they asked you to find the displacement till 3 seconds, then you add the top ones, you add these two areas, these two distances, and you subtract the one at the bottom for displacement. But for the distance, if the question were to find distance, all three of them should have been added. But luckily for us, they asked us to find till 2.1 second, not beyond that. Yeah, so here we have the next question. Sketch the variation with t with respect to time of the speed of the ball. So initially we were provided with velocity time graphs. We have to convert it into speed time graph. That's very easy. The only difference is that speed time graph cannot have any values with the negative sign, because speed cannot be negative, velocity can be negative, so this part of the graph should not be used. So from 0 till 1.1 second, the speed increased all the way to 10.5 4 and then 10.8. So at first we got to join these 2 points. So this part of the graph is exactly the same. Should raise the extra because we have to extend it only till 10.8. Afterwards, the next velocity was at 1.2 seconds, because this is the next part of the graph. The vertical line is not part of the graph. The next velocity is 1.2 at 1.2 second. How much is that? Minus 8.8. But the speed would be positive. So the speed would still be positive. How much? 8.8. So at 1.2 seconds, we have 8.8. And that speed decreases to 0 till 2.1 second. Reduces to 0 till 2.1 second. And from 2.1 second till 3 seconds, it increases again. It increases again till it increases up to 8.8. Okay, till the same point. So let me mark the point. At 3 second, it would be increased to this one. That's it. If you want to draw the dotted parts, like if you want to draw the dotted line from here up till 1.15 second, we are fine with it. But I would say just leave that part, because that dotted line or the vertical line or the one that shows the time collision is not actually the part of the graph. So you can skip that one. Let's move on to the next question. So in this one, we have to comment on the speed. I could remember the first part of it. We have to comment on the speed without doing any calculation. Initially, how do we comment on speed through velocity time graph? By commenting on the gradient. So up till a certain point, the speed, up till this point I should say. What point is that exactly? That point is at up till 1.25 seconds. Let's comment on the gradient, because we have to comment on the speed. We don't have the speed time graph, we have the displacement time graph, and speed would be found by finding the gradient, or the speed would be analyzed by analyzing the gradient. What happens to the gradient? Initially the line was steeper, it gets lesser steeper, gets less steeper, or the line becomes more and more horizontal till 1.25 seconds. So speed decreases till here. You write the same in description, from 0 all the way to 1.25 seconds the speed decreases. Here afterwards the gradient keeps increasing. So what do you say? After 1.25 seconds all the way to 3.0 seconds, the speed increases because the gradient increases. And although the direction of the gradient now it changes, but you don't say speed would now be negative, because speed is always positive. If the question were about the velocity, so you say it this way: velocity decreases, and here you say velocity increases but in opposite direction. This is how it should have been said properly. But let's see, because I could remember our question is about the speed, so we don't have to mention about the direction. Assume that the air resistance is negligible and therefore the stone has constant acceleration. Calculate for the stone the speed at 3.0 second. So we need to find the speed over here. So let's see what can be done for this. So we can use the equations of motion, the ones that we have studied already. So what if I could use the very first one? Let me call this my final speed. The speed at a certain instant of time, I'm going to call the final speed. If you could remember the very famous equation, v equals to u plus at. But then the question is, how do we find u? What is the initial velocity here? We don't have the values of velocity. I don't know the velocity. The velocity at 3.0, this one needs to be found out. This velocity v needs to be found out. I need to pick a point where I know the initial velocity, because I do know the value of g. And keep it in mind, when you use the equations of motion, you follow the convention. What was the convention? G always negative, or you can call it a. Acceleration in that case is always negative. Velocity upward would be positive and velocity downward would be negative. Okay, so do I know any point where my velocity is 0? Many of the students assume that at this point the velocity is 0. But the problem is, this is not a velocity time graph. If it were the velocity time graph, the velocity would have been 0. The velocity would have been 0 at this point only if the gradient is 0, since this is a displacement time graph. Is our gradient 0 here? The answer is no, not at all. Gradient is not 0. The line is not horizontal at this stage. The curve is not horizontal. So do I know any place where the curve is horizontal? Yes, I do know. I know very well. And matter of fact, this is the stage at exactly 1.25 second. My gradient is 0. Hence, my speed, or let's be more specific, my velocity would also be 0. So I can choose this point as the initial velocity. So my time would start from 1.25 till 3.0 second. So the value of t would be 3 minus 1.25 means 1.75 seconds. And my initial velocity is 0. Let's use this data. B equals to 0 plus the value of a should always be negative according to the convention of for equations of free fall. What was the time? 1.75. Let's write it on the calculator as it is, or you can ignore 0. So 9.81 times 1.75. Our answer should be with the negative sign because we have minus here. 17.16 minus 17.16. I can write it as 17.2. There you go. This is your final velocity, or your velocity at 3 seconds. And you know two things from here. One of the things that you know, that the magnitude of velocity is 17.2. If they ask you about the magnitude of velocity only, 17.2 meter per second, and magnitude of velocity is also known as speed. which is 17.2. But you also get additional information that this velocity is with the negative sign. Since you use the convention, according to the convention, the velocity should be negative only if the velocity is downwards. So that gives you the additional information that the stone at 3.0 second must be moving downward. This is the advantage of sign convention. Although in this one, the sign is not needed, minus sign is irrelevant because they ask for speed, which is just a positive number. But the additional information is, you know about the stone, that the stone at 3.0 is moving downward. So what could be the situation for which you can have a displacement time graph that looks like this? Let me give you the situation. You see, up till here, the displacement is positive. Then all of a sudden, after exactly how much time? After 2.5 seconds, the displacement becomes negative. So what could be the example of this situation? Example could be this thing. When you drop an object from a certain height. So let's say you have a ground here. You throw an object upward. You throw an object upward from here. Its speed would decrease as it go upward. Technically, it should be straight line, but just for reference, I'm drawing slightly to the right side. Technically, it should be here. It should travel vertically. So initially, it would go upward. This is the first stage, which is till 1.25 second. Then it comes down back to the reference point. The reference point is the one from where we initially threw the object upward. So let me draw the reference line. At exactly 2.5 seconds, it returns to the reference point, which you can see over here. And after 2.5 second till 3.5 second, it goes below the reference point. That's why your displacement is negative. We don't know how much is that, but it is negative, which means your object is now below the reference point. So this could be the situation for which the displacement time graph will look something like this.